Welcome all of you to our research project based on reinforcement learning, collaborative task decomposition for multi-agent systems. This research is focused on building a new method to utilize the collaborative nature of multi-agent systems for automated task decomposition. Before introduce our research to you, let's become familiar with the basic concepts. First concept: reinforcement learning. Reinforcement learning, RL, is a type of machine learning where an agent learns to make decisions by receiving feedback from its environment in the form of rewards or penalties. It operates based on trial and error, exploring different strategies and refining its decision-making process through iterative learning. What are multi-agent systems? Multi-agent systems are a type of computational system involving multiple autonomous agents that interact with each other and the environment. These agents interact with each other, and they try to achieve collective and individual goals. What is task decomposition? Task decomposition is a strategy used to break down complex tasks into smaller, more manageable subtasks or steps, making it simpler to handle each part separately and then combine the results to solve the overall task. So what do we propose? Collaborative task decomposition for multi-agent systems. Why do we need collaborative task decomposition for the multi-agent systems? The first reason is, the current automated task decompositions are not suitable for multi-agent systems since can't have advantage of their collaborative nature. The second reason is, the manual task decompositions are not suitable for unknown environments. And, the single agent will not encounter all possible ways to reach the goal within a short period of time. In complex tasks, there are often multiple valid approaches or strategies to achieve the goal. What is collaborative task decomposition? In the first step, each agent independently creates its local task decomposition. This means that each agent analyzes the complex task at hand and divides it into smaller, more manageable subtasks based on its own capabilities and knowledge. After creating their local task decompositions, the agents share this information with other agents in the system. After that, with the knowledge of other agents' task decompositions, the collaborative agents can now combine or merge their individual subtask decompositions. How do we implement this solution? This is implemented based on induction of subgoal automaton system introduced by Furilos Blanco and his team members. They use a LASP system as the main component in their system to generate task decompositions. At first, the agents create their own local task decompositions using the ELASP component. And then the agents share their locally created task decompositions with each other. After that, they vote for all of the shared automatons based on their experience to analyze the stability of the shared task decompositions. Then they will select the most stable task decompositions, and then they will be merged using a derivative of the breadth-first search algorithm. Let's look into the details of the process of creating local task decompositions, sharing, selecting, merging them together into a single task decomposition, and using the merged task decomposition alongside with RL algorithms like hierarchical reinforcement learning or Q-learning for reward machines. Everything begins with creating the observation traces by recording the observations encountered by the agent during a single episode. They are appended in order of encountering to create observation task. There are three types of observation traces: goal traces, which lead the agent to the goal; dead-end traces, which lead the agent to the failure or destruction; incomplete traces, which lead to none of above states. Using these observation traces, an ASP program will be created, and then by solving that ASP program using ELASP, we get the agent's local task decomposition, LTD, as a subgoal automaton. As previously said, subgoal automaton is a type finite automata. Upon updating the local task decomposition, the agent will share the newest version of the S.A with other agents. And now there is a new problem. In the POV of a particular agent, the newest version of its own LTD is stable. But the other agents have observed different set of observation traces. So, in other agents' PO versus, the same LTD may be unstable. So the agents have to determine what are the most stable LTDS out of all agents' LTDS. To do this, agents check the other agent's LTDS against their set of incomplete traces. If a particular LTD is stable according to an agent's incomplete traces set, that agent will vote in favor of that LTD, otherwise, it will vote against it. Based on the voting results, the agents will identify the most stable LTDS. And then, we introduce a new breadth-first search-based algorithm to merge these selected task decompositions. Since they are a type of state machine, we can merge them by identifying the mergeable transitions edges and states by comparing the transitions functions. Initial state, accept state, and reject state are mutual and the same for all subgoal automatons. So the BFS starts from the initial state. Then the initial state is merged at first, and the outgoing edges from the initial states of all LTDS are compared to check similarity. Upon discovering any similar pairs of transition edges, they will be merged and the resulting states at the end of similar edges will be considered as similar edges. And those newly merged nodes will be visited later, and the BFS will continue until all states have been visited. By doing this using all selected LTDS, we will get the merged subgoal automaton. After generating the merged task decomposition, the agent will use them to learn how to reach the goal. But for this we have to use RL algorithms which can exploit task decompositions. As mentioned above, most popular approaches are HRL and QRM. In HRL, they use meta-Q functions to select the best transition edge to take. And policies will be optimized to observe the edge conditions of the selected transition edge to satisfy the edge condition. In QRM, they assign separate Q function for each state of the task decomposition. But the merged subgoal automatons have non-deterministic nature. So we have to handle this. Transition tree data structure and Q-learning method are used for learn about what are the most advantageous states in the subgoal automaton. The agent will use the A* algorithm to select best state to make the next transition into, using the learned values using Q-learning. After creating the merged task decomposition, the agents can learn how to complete the task based on the merged task decomposition, and also what the most beneficial states in the subgoal automaton using a * interleaved Q-learning. We can use both QRM and HRL algorithms as reinforcement learning algorithms according to our preference that can exploit task decompositions. And when using any out of these, it gives better results than non-collaborative task decomposition methods. Let's look at this diagram which shows what are the components of the overall system and how do they interact. The subgoal automaton merging component and A* interleaved Q-learning component are the most crucial components. As previously said, the A* interleaved Q-learning component is the approach we took for breaking the non-deterministic nature. This consists of several components. Let's look into details of each component of this approach used for handling non-determinism. Transition tree. The transition tree is a specialized data structure designed to handle the non-deterministic nature of merged subgoal automatons. It's essentially a derivative of a tree, where the root node represents the initial state of the merged subgoal automaton. Each node in the tree is associated with a specific state from the merged subgoal automaton. The tree helps organize and represent possible state transitions, making it easier to traverse the automaton during decision-making processes. Interleaving A* with Q-learning. To enhance the selection of the optimal leaf node within the transition tree, our proposed approach interleaves A* with Q-learning. A* is leveraged as a tie-breaking strategy within the transition tree, exploiting its benefits for directed acyclic graphs, DAGs, like the subgoal automatons. By combining A* with Q-learning, The algorithm gains valuable insights into the proximity of each leaf node to the accepting state, which aids in making decisions during traversal and path selection. In summary, our proposed approach combines the benefits of the transition tree, a star algorithm, and Q-learning to effectively navigate through the non-deterministic nature of the merged subgoal automatons. By leveraging a star as a tie-breaking strategy and using Q-learning techniques to update edge and state Q values, the algorithm demonstrates promising potential for enhancing decision-making processes in handling non-determinism in merged subgoal automatons. What are the benefits of CTD? According to the evaluation results, in MASS, CTD provides faster learning and increased average reward. Collaborative task decomposition allows agents to explore a wider range of possible strategies and share their experiences, leading to faster learning and convergence to more stable and effective task decompositions. This collaboration enables agents to discover better paths to reach the goal earlier, resulting in increased average rewards compared to non-collaborative methods. Resource efficiency. This will save computational time by reducing the training time, and also will reduce material costs caused by the accidents which cause the destruction of the agents in real life. This resource efficiency makes the system more practical and scalable, especially in resource-constrained environments or applications. Enhanced adaptability to new environments. Collaborative task decomposition allows agents to pool their knowledge and expertise, making it easier to handle unknown or changing environments. The collective analysis of the environment and the sharing of insights enable agents to quickly adapt and respond to new situations, reducing the time needed for exploration and increasing the system's ability to tackle novel challenges effectively. When compared with non-collaborative task decomposition methods, hence, we can come to the conclusion that our new collaborative approach is better for automated task decomposition for MAS, rather than using non-collaborative systems. Thank you for watching.